Okay, so far we have talked about integrals that are continuous functions on closed intervals. Okay. If a function has been continuous on a closed interval, we have been able to find integrals. Okay? Now, sometimes we may have an infinite function that we want to find the antiderivative of, or we may have infinite limits. And that is why we have what's called improper integrals. Okay? So let's say that f is continuous from a to infinity. Okay? To find the area under the curve, we have to have a continuous function. Okay? Well, we have to have a continuous integral. Let me rephrase that. Okay, if we're going to do an integral, we have to have a continuous interval. Now, if I say, all right, let's find the integral from a to infinity of f of x dx. We can't necessarily just like plug in infinity, but we have this concept of a limit. Okay, so what we can do is we can replace infinity with a different letter and take the limit as that letter goes to infinity of our integral. A is going to be a number. B is just going to be B or C or D or F. Probably not F, but whatever you want within reason. Okay, I'm probably going to use A, B, and C.
Can I make it an emoji?
No. Now, not all the time will we get an actual, do we always get numeric values for our limits? No. Sometimes we get like infinity or negative infinity. Okay? If we actually get a number from this limit that is representing the area under the curve, okay, or that's the actual value of the integral. If we get an infinity or negative infinity, we're going to say that our integral diverges. Okay, there's it's an infinite area essentially. Okay, we can do this then. For like negative infinity to A. Okay. In this case, we would just replace negative infinity with a letter. For fun, I'm going to choose C. Okay. And then you would evaluate this integral, and with that antiderivative, you will evaluate the limit.
Wait, I see you put infinity or negative infinity?
There should be a negative there. You just can't see it. Now, some of you may be wondering, what if we have the integral from negative infinity to infinity? Ideas?
Wouldn't we just do an indefinite integral?
No. Good idea. what we would have to do is we would have to pick some value in between negative infinity and infinity. And we would have to break this up into the integral from negative infinity to, we'll say c, and add it to the integral from c to infinity. And then you would have to work with two different limits.
Okay. And what is an indefinite integral if you can't use the indefinite integral here?
Well, an indefinite integral is just giving you the antiderivative.
Yeah, I was just looking at the other curve.
No, because there's no values. The antiderivative is just the antiderivative.
Okay.
Only a definite integral gives you the area under the curve.
Okay.
Okay.
So what happens when you've got discontinuity?
We'll get to that in a little bit. Let's work on this first.
Why do you have to break it up? Couldn't you just like subtract the limit, like, so subtract the limit of negative infinity from the limit of positive infinity, like, all in one?
No.
Okay.
Because we can only replace, like, we have to replace infinity and negative infinity with, like, a letter. And so if we have to replace both of them with a letter, we have two different, oh, I see what you're trying to say.
Like you find the antiderivative and then you plug in the values at positive and negative infinity to like actually evaluate it.
Yeah, but we need to write it as a limit. Okay. And evaluate the, I mean, essentially, yes, that's what you're doing, but we need to actually, like, use our calculus and write it as a limit, because there may be times where we have to use, like, I don't know, do a Hopital's rule, when we evaluate a limit. Okay, so maybe a little bit official. Okay.
I was just destroying the purpose of this class. Anyway.
Okay. What does this mean? What does this represent?
We're finding the area under the curve of the function 1 over x squared from 1 to infinity.
We're finding that area. So it's going to keep going, right? What? Do you have a question? Caleb?
Is the end result to get decimal answers or just like an equation?
The end result is either going to be a number or divergence. And I'll show you both cases if you are patient.
I don't know, maybe.
All right, so first of all, is this a continuous function from 1 to infinity?
Yeah.
Okay.
Sure is.
Let's pick a letter to replace infinity with.
Hey.
A sounds great. And so we're going to write the limit. The limit as a approaches infinity of this. Okay. So we have the limit as a approaches infinity. What's the antiderivative for 1 over x squared?
Negative 1 over x.
So we have negative 1 over x evaluated from 1 to a. Okay, so if we evaluate our negative 1 over x from 1 to a, we're going to plug in a minus plug in 1. And now we have a limit, we have an expression that we can take the limit of. As a goes to infinity, what happens to negative 1 over a?
0.
It goes to 0. And the limit as a approaches infinity of 1 is 1. The area under the curve from 1 to infinity converges to 1.
Or it diverges in another case.
If this were infinity, then we would say it would diverge. Okay. So our area, yes, it's an infinite area, but it's converging to 1. The more area we add, the closer and closer and closer we get to 1. Let's try another simple one.
Nothing.
Okay. Okay, does this one look much different?
Yes.
No,
Yes.
not
Now
much.
you have to deal with natural
Not
numbers.
Yeah. Okay, so it's the same interval. The function just differs by a degree in the denominator. Okay. We are continuous, so this is okay. What do you want to replace infinity with?
Here.
Q.
Very well, I think it is.
Okay, so we write it as a limit. Now we can take the antiderivative. Zach is very excited about this.
Here's the case.
What?
I was confused. Here's the case.
Someone want a Q.
It's okay, just some weird variable for that.
You don't have to use Q in your notes then.
Okay.
What is the antiderivative of 1 over x?
LNX.
So we have the limit as Q approaches infinity of the natural log of Q minus the natural log of 1. Well, what's the natural log of 1? 0. We're not worrying about that right now. What about the limit as Q approaches infinity of the natural log of Q? That goes to infinity. Remember what the natural log graph looks like? So towards infinity, the natural log continues to grow. This goes to infinity, which means our limit is infinity, which means this integral diverges.
So all of these integrals where you probably can be non-calculated, it's all gonna be like nothing good.
Yeah, there's really no way to do this.
And a really big number.
Yeah,
we ever-
I was excited, don't want to see that.
What if we get something where we have infinity minus infinity as our limit?
Well, then you go
Then that would be a L'Hopital problem.
Draw a little ambulance and keep on trucking.
That is why L'Hopital's rule came before this thing.
Oh.
You will need to use it. Moving on. All right. Is this one continuous?
Yes.
Yes.
Okay. So we have both limits that are.
Two letters.
Well, first let's break it up into two integrals. Where do you want to make the break? 0 sounds fabulous. So let's write this as the integral from negative infinity to 0 plus the integral from 0 to infinity. Okay. Now we're going to need to choose two letters. How about A and B? Sounds wonderful.
you're gonna do it anyway, but.
It's 0 now, it's scheduled first.
What?
I didn't even hear what you said. Okay.
We have two limits, but luckily we're on the same antiderivative. So we broke it up into two integrals. We replaced our infinities with letters and written them as limits. What's the antiderivative of 1 over 1 plus x squared? Fair warning, this is not the last time you will see this in this section. This is just the arctangent rule. What did you say?
Just saw like the.
Okay. So we have the limit as a approaches negative infinity of the arctangent of 0 minus arctangent of a. That's the limit as e approaches infinity of arctangent b minus arctangent 0. It is important that you understand what the arctangent graph looks like. Can anybody describe to me what the arctangent graph looks like?
Is it sideways tangent?
Inverse tangent looks like this. What is it approaching here?
Like.
Think about tangent and where the asymptotes are for tangent. Mm-hmm. And negative pi over 2. I'm telling you right now, you need to know what this looks like, so you can evaluate limits that involve arctangent. Because this will not be the last time you see a limit that involves arctangent in the infinities. Okay? So, what's the arctangent of 0? 0. Okay? So right now we have 0 minus, what's the limit as a approaches negative infinity of arctangent of a? Okay, so this is going to negative pi over 2. Limit as b approaches infinity of arctangent of b. That goes to pi over 2. And the arctangent of 0 is 0. So the area after that curve is pi. We are going to have to do the same thing if we're looking at discontinuities on an interval. And these discontinuities can only appear at the endpoints of an interval.
So if you have a bunch of discontinuities, could you just take a bunch of smaller intervals and treat those?
Well, but you still need to, well, if we think about,
Like take the points where it's like, okay, it's discontinuous here, and just take intervals.
well, the problem is going to be, they're going to be continuous between A and B, but like that first interval, it's not going to be continuous at A. Like for example, 1 over x has a vertical asymptote at x equals 0. If I ask you for the area from 0 to 1,
It would converge
Okay.
to some number, wouldn't it?
it would. However, we can't just plug in 0 because it's undefined there. So we have to write it as a limit as some numbers approaching 0. Okay. Now, the only thing that I will warn you, okay, let's look at the cases of A to B and A to B. We are still going to do this concept of a limit. Okay. However, when we have intervals with numeric values, where we have discontinuities on an endpoint, we're going to have to write them as either a right or a left-hand limit. Okay, so in this case, we have discontinuities at A. So A is what we are going to need to replace here with some letter, and we're going to write the limit as C approaches A. Is it a right or a left-hand limit? What's your rationale?
Because it's like, it's going from A to B.
Like, if we think about, okay, this is our endpoint. We want to get as close to A as we can, so we have to come from the right, since that's where our interval begins, right? We only have numbers to the right of A, so we can only approach A from the right. So that means when we make this integral, since B is where our discontinuity is, we would replace B, and we would have to make a left-hand limit because the values in our interval are all to the left of B. We all know how to evaluate left and right hand limits, right? For the most part, it's not going to be an issue. Okay, most of them are going to be pretty straightforward. Fun? Yes. He is not here. He probably won't come to my class. So yeah, you could probably just start with his third hour. Okay.
Dustin for such a bad student.
What would you guys most like to
It's not hers.
I know. I'm aware. I did text Dr. Ford and ask him if he was sick, but I don't think he texted me back. He said I won't be there.
Wait.
What?
We did the
Probably not.
A to B including B,
Oh,
A to B including A and B, just B to A and B.
Okay, so what are we gonna do if we have A to B where A and B are both not included?
Just negative.
Split it.
We would have to split
Like
it
the infinity one.
like the infinity one. If an endpoint is not included in our domain, we can't plug it in, and so we have to do a limit.
So do we just like combine the first and the second?
Yeah, kind of like we did with the two infinity rules.
Can you write that please? I'm not good at thinking abstractly.
I'm just over here.
There you go, a lot of letters thrown in here. You'd have to break it up like we did with our infinity, negative infinity to infinity. And then from there, since these are not included in the domain, then you'll need to make those limits. Does that help? Okay. In this problem. What is the issue with our limits of integration? Okay. One is where we have a vertical asymptote. So instead, we're going to have to write this as the limit. Okay. What would you like to replace 1 with?
P2.
A sounds great. There's too many letters. I picked my favorite. Right or left-hand limit?
This would be a right hand.
Right-hand limit because all of the numbers in our interval are to the right one. Okay. Now, we can actually take the antiderivative, which is what? Natural log, yeah. Natural log of 1 minus x times negative 1. Right?
One minus 2 to some 1. Oh, it's okay.
Okay. Let's think about, well, what's the natural log of 1?
0.
0. Okay. We need to think about the limit as a approaches 1 from the right of the natural log of 1 minus a. Natural log of 1 minus a, what does it look like? Okay, it's moved to the right and it's well, it's moved to the right one and it's reflected. What kind of reflection? No, that's not right.
Well, okay.
That doesn't matter.
Wait, are we not going to get calculators for this? Because there's no way I can graph this on my own.
You can do it.
Oh, I don't. Guess I'm trying to remember that minus a negative.
No, just in
Here's
case.
graph of it.
Oh, what did I forget? Oh, I didn't
Grass
get
look
that.
like anymore?
This has been like 5 years.
Yeah, you get oil and gas like all the time, you just don't want it. Do something wrong.
Are we gonna need to know how to actually wrap it into quiz or test?
Well, you don't, are you telling me you don't know what the natural log looks like?
No, because.
I don't know how to like reflect it and translate it and stuff. I don't know what it usually looks like.
So it's basically.
Okay, so let's think about this.
I am already maybe.
If it's towards infinity, the natural log is either going to go, the natural log is going to go to infinity or negative infinity, right? If it's towards an asymptote, like in this case, where's it going to go?
Asymptote.
Infinity or negative infinity,
Yeah.
right? Okay.
But I don't know what form.
Whether it's infinity or negative infinity, it's going to diverge.
We try divergent.
Divergent.
Diverges would be better.
Divergent.
Okay,
It is a divergent integral,
so,
or an integral that diverges.
Say a divergent in an interval that diverges.
I feel like it's integral.
A divergent,
Yeah.
a divergent interval is divergent.
so does that mean that limit just equals infinity? So as you look at it,
A little, I need to come back. I need to come back to this. Okay. I need to come back to this. Something's gonna click and I'm gonna come back to it. Okay. Okay, I have an answer. Sorry, I was thinking. So y equals the natural log of 1 minus x with all of our the reflections. We decided it looked like that. Since there's an absolute value, we can also plug in the other side. So that's why we can say that this is
Exactly.
negative infinity. Okay. I'm sorry, that took me a little bit to think about that. Okay. What's this issue?
And it's somewhere in the range, which is x equals 1.
We have a discontinuity at 1. So we need to break this up at 1. So I'm going to write this as the limit as A approaches 1 from what side? plus the limit as b approaches 1 from the right of b to 3.
They have to be different variables.
Yes. That is a great question. Do have to be different variables.
Railroad students for that one.
Nothing. What is the antiderivative of 1 over x minus 1 to the 2/3? Okay. X minus 1 to the 1/3 divided by 1/3, right? So the limit is a approaches 1. Alright, so we have two limits to evaluate here. We have the limit as a approaches 1 from the left of 3a minus 1 to the 1/3 minus 3 times negative 1 to the 1/3 plus the limit as b approaches 1 from the right of 3 times 1 to the 1/3 minus 3 times b. It does not matter if we're going from the left or if we're going from the right. What is the limit as a approaches 1 from the right or left of 3 times a minus 1 to the 1/3? That limit goes to 0. This limit goes to 0. And we have a positive 3 plus 3, which is 6. Oh, did nobody stop me there? Shouldn't this be 2 right here?
You silly goose.
I plugged in 2 instead of a 3.
Oh no.
Wait.
We have to plug in 3, and 3 minus 1 is 2.
Okay.
And I said 3 minus 1 was 1, which would have been really cool, but... What's that? What?
It's not on the sheet.
Yeah, you guys haven't been very good at pointing those things out at me.
I was still writing the problem.
Oh, from up there?
No, like the sheet second one.
Okay. You were gonna catch it though, right?
I just got it. Yeah.
Alright, so your gold sheet has your homework. It's 9:41. We have 10 minutes. I expect you to get a problem done before you leave.
That's a lot. Josh didn't. I asked Josh why I wasn't here, and he said doctor. So.
Okay. We miss you, Josh.